Okay, so we have finished two goals so far. The first one was to show that every finite dimensional algebra, studying its representation theory is just like studying the representation theory of bound Quivers. That was our first goal, and the second goal was to formally define what is the Auslander-Reiten quiver. We did that via the notion of the radical of the module category, and we said that if m and n are indecomposables, then rad mn modulo rad square mn, that will tell us how many arrows to draw from the vertex m to vertex n in the Auslander-Reiten quiver. So now we are proceeding towards the main goal of this whole lecture series, and that is introduction to Auslander-Reiten theory. And we are skipping a lot of proofs, but also trying to make it self-contained in a fashion. So we started with a bit of homological algebra, recalled what projective and injective modules are in terms of home functors, exactness of home functors. The covariant one gives us projective and contravariant one gives us injectives. And in general, if you think about general rings, then projectives and injectives are very different. However, in the case when A is a finite dimensional K algebra, which is our base assumption over here, we can observe that they are very similar. In fact, they are in one-to-one correspondence. So let me quickly recall that we know that projectives and injectives in this case are closed under finite direct sums and direct summands. And then we define what is the notion of a projective and injective resolution, global dimension. And the main topic that we covered yesterday, relevant to today's lecture, that was the Nakayama functor, which we defined as the composition of two dualities, two contravariant functors. The first one is home blank A, and the second one is the standard duality on vector spaces that we do. That is home blank A. So home blank A goes from A mod to mod A op. It's a contravariant functor, and it goes from mod A op to A mod. And both of them are simply compositions with certain morphisms, and the composition of both these functors, which we denote by the letter nu. This nu is actually a duality when when restricted to projective modules. It gives us an equivalence with injective modules. Which is a surprising thing because normally this doesn't happen in practice. Okay. So any questions on yesterday's material? This is where we stopped. Okay. So we can perhaps proceed. So D is a duality on, then we have to ask, if we are calling it an equivalence on categories, then let's try to understand what it does to morphisms. So let's take a projective module, Pi, and what is the corresponding module, that is II, injective module at I. And then if we have Pj, Pi to Pj, there is a map, and these maps are, they have to, so if there is a path from I to J, then usually what we do, we have a map from Pj to Pi, which is by composition. Am I saying it correct? Just wait. Okay, just hold on. Maybe I'm not saying it right. So what I'm saying, in one case, you have to compose with a path. And in the case of injective modules, you have to cancel out a certain path. Does that make sense? So that is how nu acts. on maps. So, and we also have to talk about this inverse. Yeah. So the
Sorry.
inverse of the, okay, we have somebody speaking.
Yeah, so
Yeah, Bappa.
can you please display your screen?
Could I please display my screen?
Yeah, I mean, so we can't
Is my
read
screen
it.
visible to others?
Yeah,
It's
yeah.
It
fine.
is
Everything is
visible but
fine.
Yes, it
very
is visible.
small.
No, I
Like
think it's fine. It's visible.
No, it's
Should be fine.
It's
it.
visible and small.
as in
Yeah,
like
so
it is your video and the screen that you're presenting coming next to each other, and that what you're presenting is in like smaller than what usually it should
I
be.
think I think
Yeah,
that
now
is
it
video
is
setting
better.
maybe because
Now it's better. I have removed
yeah,
Yeah,
it's
my
okay.
now it's
spotlight.
good. Yeah,
Yeah,
Yeah, that spotlight was mainly for recording, but let's hope that it's not a problem. Okay, thanks, Shraddha and others. So, okay. So what I'm talking about now is the inverse. Because it's an equivalence, we also have to understand the inverse. And well, you have to spend some time with it uh, and figure out that the inverse, new inverse is home. It's a home functor, but it's a covariant home functor applied on the dual of the right regular A module. And I'm sure you will figure it out if you work it out. And what is this dual? I mean, you just do the computations because A is isomorphic to this direct sum of all the projectives. A op is isomorphic to this, obviously. And what will this be? Yeah, this is the right regular A module, which is I mean, in uh, home preserves direct sums in both components. So we can simply take out the direct sums from both components. Yeah? And we are doing that here. So we take out PQ op I, comma K, and that we have seen is just the injective module corresponding to this. So this is nothing but the direct sum of all the injective modules. If you remember earlier, then yeah, I mean, home A blank is this. Yeah, A is isomorphic to the direct sum of all the projectives, whereas this other object, DAA, is isomorphic to the direct sum of all the injectives, which sort of makes sense. Yeah, I'm not going to prove this, but hope this is clear. This idea is clear.
Excuse me. Did you mean
Yes.
IQ in the opposite category?
No. After applying dual, you will actually get IQ.
Ah, that's true. Okay.
Yeah. So let us see this. So home blank A, if you recall what home blank A is, it's a contravariant functor, but we wrote on the first page itself that it is left exact. Yeah, left exact in both components. Whereas the duality simply swaps everything. So therefore, the composition of the duality with this left exact functor will give us right exact functor. In fact, if you know a little bit of homological algebra and tensor products, then you should be able to write the Nakayama functor as a tensor product. And then it is rightfully justified that it is a right exact functor. Okay, so how are we going to use these things? In general, we know that the global dimension of an algebra could be infinity. Even a bound Quivers algebra could be infinity. We saw one example yesterday during the tutorial where the global dimension was actually infinity. However, at that time, Isha also mentioned that many times if you start thinking about what projective module surjects onto your given module, then the most natural choice will turn out to be a minimal choice. It will be the minimal projective module which covers it. So this is the definition of projective cover. Okay. Dually, it's injective envelope. So let us try to understand what we are doing here. So we say that a submodule n of m is superfluous if you take any other submodule n dash, and if the sum of n and n dash is m. I'm not talking about direct sum here. I'm just talking about the sum. If the sum of n and n dash is m, then actually n dash has to be m itself. So nothing apart from the full module can complete this proper submodule. Maybe I forgot to mention that it is a proper submodule. So I should write that. Yeah. So say that a proper submodule, yeah, is superfluous if the only thing that can complete it is the full module itself. Well, I will show you examples. It's not easy to come up with random examples of this sort. And projective cover is this short exact sequence essentially, where P is projective and the kernel of this surjection is superfluous submodule. So in some sense, we are saying P is the best. It is the minimal one which covers this. If it is not superfluous, then it will have something which can be separated from N. And yeah, so we are trying to capture that particular idea. So look at this simple enough example. Yeah, all the morphisms here are written horizontally, and the modules are written vertically. So we are talking about this A2. It's a two-element, two-vertex quiver, and we are taking this particular module. It is a non-projective module. We have to ensure that. Otherwise, what will be the projective cover of a projective module? Any guess? Just to see if everybody's, yeah, awake. It's just itself. Yeah, identity map is the projective cover. I mean, we are using category theoretic language, so I always prefer to talk about maps rather than objects themselves. Okay. So, however, this K0 is not a projective module. So therefore, now let us think about it. Yeah, which projective can cover it? Well, obviously, if we are talking about this, then there are only two projectives, namely 0K, which is P2, and KK, which is P1. There are only two projective indecomposables, and KK will cover it. And then observe what is the corresponding kernel. The kernel happens to be 0K. This is just dimension vector computation. Now, if you observe, then the projective module P1, namely KK, doesn't have any proper non-zero submodule other than 0K itself. Okay, it's the unique proper non-zero submodule. So what can be added to 0K to obtain KK? The only thing possible is KK itself. Yeah, so this is superfluous. Do you agree with this like very basic example, a very preliminary example? Maybe we'll do one more example of this sort. But do you agree that this is a minimal projective presentation? Yeah, or a minimal projective resolution of this? Well, what is minimal projective resolution? You simply keep making a choice of a projective cover at every step. Let me quickly remind you how we constructed projective resolutions. We started with M, then we took this surjection from P0. Well, we choose this to be a projective cover. Then we obtained kernel. Then for kernel P1 to kernel epsilon, also we will choose it to be a projective cover. And you keep doing this. And whatever you obtain in this fashion is actually a projective, minimal projective resolution. Now, is it unique
May I
or
ask a
not?
question?
Yes, Irfan?
Yeah. So, I mean, I don't still understand why do the projective covers exist in the very first place? Is it guaranteed?
Yes, that's my next line exactly. Yeah.
Oh, I see. Go ahead,
In
please.
in this case, we know that projective covers do exist. Well, here is the idea. If you are given one particular module M, then dimension of the component vector spaces MIs is still finite. So what you do is you take a direct sum of dimension MI many copies of PI, and this will be a projective cover. Well, let me write that. Yeah. So I have left some blank space here. If K is equal to KQ, then first of all, let us try to calculate the radical of PI. Well, do you remember what Pij is in this case from Upendra's lectures? So Pij, what is the K span of? Somebody please.
All paths starting at I and ending at J.
Yes, K span of, yes. Can you please repeat? I couldn't hear you.
Paths starting at I and ending at J.
Okay, K span of the set of paths. From I to J. Well, here I'm assuming A is finite dimensional, so therefore A is acyclic. Yeah, let us make our life simple for now. Now, what is the radical? I already told you what radical is. No, sorry. We only discussed radical of the algebra. We did not discuss the radical of the projective module. So, radical of the projective module PI, this whole thing evaluated at J, it will be, well, it will be the same as Pij if I is not equal to J, and we just have to remove the top. And what is the top? The lazy path at vertex I. That is the only thing we have to remove. So the dimension will be, the codimension of radical would be exactly 1. So I'm just going to write 0 if I is equal to J. Because I said that A is finite dimensional, so therefore the quiver Q is acyclic. So there are no loops possible from I to I. All right. So yeah, somebody wants to say something? No.
I had a doubt in the previous example.
Yeah.
We are trying to find the projective cover for K0, the module
Yes.
K0. And we take KK to be the projective cover and 0K to be the kernel. So why is 0K superfluous? I do not understand why is 0K a superfluous submodule in this case.
Okay. So can you tell me all possible submodules of KK?
Why wouldn't K0 also be a submodule of KK?
Okay, maybe I should write this now, because you are confused about this. I'm going to use a red color, and well, I will write this in this space. Okay. So if you think about this commutative square, yeah, M and P and 0, will this commute in general if M and P are non-zero?
No.
Exactly. So that is precisely the idea we are using. Yeah. So the module you are talking about K0, and you are asking whether it is a submodule of KK, which means there should exist maps like this which make the diagram commute. And that is not possible. Yeah, the indecomposability, the beauty of this whole theory is that these two copies of K are held together by an identity map. And even if you were doing this, this kind of direct sum, yeah, if at all they both were sitting inside kk, both were submodules of kk, then what will this direct sum be? It will be kk, but with a zero map in between. Now, the zero map doesn't allow us to go anywhere.
Yes, yes, sir, I understood it.
Okay. So that's precisely the point that you, okay, so in any commutative diagram, yeah, please remember that if there is a zero, then that should be on the main diagonal and not off diagonal. If the diagonal entries are non-zero, then the off diagonal entries should also be non-zero in order for it to commute. A very simple observation, but very powerful. Okay. So let's come back to the example that we are trying to compute over here. So I was saying that because Q is acyclic, there is no path from I to I apart from the lazy path, and therefore radical of Pi evaluated at I, the ith location is 0. Otherwise, what will you do? If it is finite dimensional and let's say it's a bound quiver, what will you do in this case for the radical? You will simply remove, yeah, from PII, you will simply remove the lazy path. You will still reduce the dimension by 1. Yep. Only the lazy path needs to be removed, and that's the radical. You can verify that. And the radical obviously embeds inside sorry, not this, not with a J, but just, yeah, radical embeds inside Pi. Okay. So what I was referring to here is K0. Yeah, K0, what is the dimension of the vector space at location 1? It is 1. And location 2, it is 0. Yeah. So we actually just took the projective module at vector 1, at position 1, at vertex 1. So P1, one copy we chose. And then the corresponding kernel, in this case, turned out to be the radical of that particular projective module. So can you see that radical of P2 in this case is actually P1? Yeah. We just took that in this case. Yeah.
You meant radical of P1 is P2.
Oh, sorry. Yeah. Radical of P1 is P2. Yes, thanks. Okay, so in general, what will happen? Now try to think about this. Yeah, this is our projective cover. So I'm starting with some M, then I'm taking 0, and this is direct sum over all the vertices of dimension mi many copies of Pi, and this definitely maps onto it. What will be sitting inside over here? Recall that we are talking about an acyclic quiver and a path algebra. So in this case, it is hereditary. So I just want to give you a flavor of what this kernel could be. The kernel has to be projective because it's a submodule of a projective module. So which projective modules will appear in this case? Okay, if you can't think about it, let me draw some picture. Yeah. So let's say this is I, this is J1, this is J2, and this is J3. And I have got something like this. Now, when I'm taking the radical, what happens? Well, this I is the piece that is connecting everything together. Do you agree with that? I keeps everything connected together. As soon as I drop that I, what am I going to get? I will get the remaining arrows. I will break all the arrows. I mean, I will reduce the length of all the arrows by 1 because I'm dropping I. So I will get, well, this radical of pi in this case would be, do you agree with me that it will be P of J1 direct sum P of J2, J3, P of J1 and P of J3. Yeah, any questions? Okay. So the same thing we have to do in this case. Yeah, so first of all, we have to understand what this map is. Yeah, what this map G is, let's say. So dimension mi many copies of pi. Well, all those copies have one generator, namely I. So we are going to send ei, the lazy path at I. Yeah, the collection of all the lazy paths. So ei1, ei1, ei2, and dot 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 ei dimension mi, which I'm writing as di. We will map it to a basis of mi. Yeah, so we have chosen dimension mi many copies of pi. So we'll map this to a basis of mi, and that will extend to a morphism. Yeah, that's not hard to see. And we are doing it for every vertex I. Yeah, that's how we obtain this projective cover. And now we are trying to find its kernel. Okay. So what did we do in this case? So recall this particular example. We had arrows alpha 1 and alpha 3. We basically took the targets, all those arrows which had source as I. We took their targets and we took the sum of all those projective modules corresponding to the targets. So we have to take the direct sum of the projective modules of corresponding to the targets, but how many times? And what should be the sum indexed by?
It should be again dimension mi many times because each of them we have taken it.
Again,
And
dimension of?
Dimension kmi, dimension of mi.
Think about it. How many times did it appear? Well, however many times it appeared, like I'm just going to so dimension of ms alpha actually those many times, and we are going to sum over all the arrows. However many times this radical appeared, yeah, we are supposed to remove it.
So I was thinking to write this sum over I naught, I and Q naught. Over
I
all
and
the
Q naught. Okay.
Yeah.
Yeah, I think that can also be done, but this is also a valid expression.
Okay.
Yeah. And because we are talking about hereditary algebra, so we close this over here. Yeah, so this is a two-term projective resolution of n. Okay, any questions related to this part? Like we are
I have one. So
yeah.
So I mean, I wonder what would happen if you reverse the arrow from I to J3. I mean, so suppose you had an arrow from J3 to I.
And
then will
I
the
mean,
radical
it will be a
be
totally
G1
different
only?
quiver.
Yep.
Yeah, I'm not sure what your question is.
Yeah, so then will the radical be isomorphic to PJ1 only? Only the targets?
I mean, as long as we are not taking any relations and not introducing any cycles, you have to repeat the whole procedure for that quiver.
I see.
So, okay, I think maybe I understand your question now, that if you reverse the direction of J3, arrow alpha 3, then you are asking what will be the radical of Pi in the new quiver.
Right.
And that will just be P at J1.
J1. Yep. Yeah.
Yeah.
Yeah, that
Is
is
that
what I was
satisfactory?
suspecting.
Yes,
Yeah.
it should just be P of J1, because we are talking about all the arrows which are leaving I. So in the new quiver, alpha 3 is incoming, so we shouldn't consider it.
True. Thanks. Yep.
Okay. Fine. So I just wanted to give you some flavor of what these minimal projective resolutions are. They are also called standard projective resolutions.
Oh, by the way,
We are,
sorry.
yeah.
So why that is a projective cover? I can see that it only
You have to
suggests.
prove. You have to prove it.
Okay.
Yeah, I'm not
I see.
claiming that it's obvious. You just have to prove it. Okay. So this is a minimal projective resolution, and that sort of removes our dependency on which projective resolution we are choosing, because we saw yesterday that projective resolutions are not necessarily unique. Yeah, we saw some examples of that also during the tutorial. I mean, I can simply take any projective resolution and add something else. Yeah, so let me show you something. So I take up, this exact sequence, P0, P1, and so on, P2. Yeah, this discussion is also useful. And then I'd simply add a copy of Q. And when I'm taking a morphism, whatever my original morphism was, I will take F1, 0, 0. This is still F0, but this is F1, 0, 0 and identity on Q. Yeah, I can simply add that in between, and that is not minimal anymore. Okay, so that's why minimal projective resolutions are some canonical choices. And moreover, I'm also giving you an explicit choice of a projective cover. In the case that A is a finite dimensional bound quiver algebra. This removal of uncertainty is essential, because now we want to try and understand what is Auslander-Reiten translate. Okay. So now recall that given any particular module, a minimal projective presentation, a minimal projective resolution can have infinitely many terms. However, we have to truncate it. Yeah. If you have studied a little bit of module theory, then a presentation of a module, yeah, we talk about finitely presented modules. So we talk about finitely many generators and finitely many relations. So we start with the module M, then we say R to the power N over here and R to the power M. So this first one which maps onto it is called the set of generators are the basis elements here, and the set of relations is the second one. So similarly, we are simply truncating our minimal projective resolution at this second step. After P1, we don't take anything. And that is fine, because our Nakayama functor is right exact. So it will preserve the zero at the end. Even if there is a zero present in the beginning, that doesn't matter. So we are applying Nakayama functor on it. Okay, what do we get? We get nu m. It doesn't change direction, so we'll get nu m to 0. that is still preserved, then new P0, new P1, and then whatever this map is, yeah, maybe I should write this, write the names of this. This is new F1. So new kernel of new F1 we put and then we complete. Okay, we simply complete the map, the exact sequence. And this kernel of new F1 is what we are defining as the Auslander-Reiten translate of the module M. I mean, a priori, if you just look at this, then yeah, that doesn't make sense. Yeah, what exactly are we doing? But remember that new M is not really important here. What is important is we are talking about a map between two projective modules, two finite dimensional projective modules, from which we can recover M as the co-kernel of the map F1. Yeah, we can recover M, co-kernel object of map F1. And then new takes projectives to injectives. So new P1 is injective, new P0 is injective, and we are talking about a map between them, new F1. So it's a map between injectives and we are taking a kernel. So if you, the more you think about it, it will become clear that this process can just be done, I mean, in both ways. Yeah, you take a map between projectives and then you obtain a map between injectives. One side you take co-kernel and for injectives you take a kernel. So this is the so-called Auslander-Reiten translate. Well, the first thing that you should notice is if M is projective, then what is its projective presentation? Well, obviously you can choose P0 to be minimal projective presentation will always give you that P0 is isomorphic to M and therefore P1 is 0. We don't need any relations. So P1 is 0. So therefore new P1 is 0 and new F1 is a 0 map. And well, the kernel of the 0 map from 0 is 0. So therefore, the Auslander-Reiten translate of a projective module is 0. Okay, so we can do the reverse process as well. We can find the inverse Auslander-Reiten translate, which will write as tau inverse. So you start with a minimal injective presentation, 0M I0 I1, and apply the inverse Nakayama function now. And do the same procedure. Now you have obtained new inverse I0 to new inverse I1, a map between projectives, you take its co-kernel. I mean, the new inverse M is not playing any role here and new M is not playing any role here. All we really care about is this middle thing. Are you okay with these definitions?
Yes, yes.
Okay. So let us compute one example. So I'm going to consider this particular quiver, this particular version of A3, 1, then 2 and 3. Well, hopefully you all remember what the indecomposables are. Yeah, they are written using their dimension vectors. So let us compute something for a non-projective module. Yeah, we want to compute the Auslander-Reiten translate. For non-projective only we can do it. So I'm choosing the non-projective 100. We will see the whole range of things. So 100 means it is the simple module at vertex 1. Well, can you tell me what its projective cover should be? Simple module at 1.
Should just be P1.
P1, okay. So what is P1? What is the dimension vector for P1?
So the 110.
110. Thank you. And what will be the kernel of this? Kernel of this map, I mean, just look at the dimension vectors. Yeah, there isn't much to think about. It's just going to be the simple module at this simple module as well as projective module at vertex 2. And then there is a 0 as well, but that 0 doesn't matter. This map is injective. And because 0, 1, 0 is projective, we need not go further. We don't have to take a projective cover of 0, 1, 0. Okay. Now let us apply the Nakayama functor on this. So this is, as I should just recall that this is P2 and this is P1. And all we care about is this inclusion F1. So the corresponding, after applying Nakayama functor, you will get I2. And what is I2? Well, I2 is simply 1, 1, 1. All the arrows coming in at vertex 2. And at P1, all the arrows coming in at 1. So that is 1, 0, 0. And then we have to take the kernel of this new F1. This is I1. Kernel of new F1 will be 0, 1, 1, because that's the only map possible between these two. Yeah, it's a surjection, and that's the only map, and we have to take the kernel as this 0, 1, 1, which is the Auslander-Reiten translate of this. This was our starting point, and this is our end point.
I have a
Now,
question.
yes.
So like as the notation is suggestive, do we get tau tau inverse is identity?
I will come to that soon.
Okay.
Yeah, not always, but in some
Mhm.
cases, yes. Okay. So similarly, we can do another example as well. I mean, if we start with, or maybe I did a very boring example. Well, I'm not going to do tau inverse example. Yeah, you can do that. You can actually just follow this whole process and compute. I'm not saying the computation is easy. Yeah, however, I'm saying the computation is possible. Like theoretically, this is how the Auslander-Reiten translate and inverse is defined. And if you compare it with the theory developed in first week, the Coxeter functors. So Coxeter functors will kill, I think C plus kills projectives and C minus kills injectives. So compare that with this, because this is still a finite representation type thing. We are talking about the path algebra of an acyclic quiver. So you should verify that the Coxeter functor applied on 0, 1, 0, 0 is indeed 0, 1, 1.
So I have one small.
Mhm.
Okay. So we have all the 6 indecomposables on our screen.
Yes.
And during in the tutorial, we have drawn the AR quiver for this type, which is
Yeah.
like,
Yeah.
right?
I will show it. I will draw it. Yeah, you can talk.
Okay.
Mhm.
And you said something about it, something about AR translate in terms of the picture.
AR translate. Yes, yes. So maybe
Can
I
you-
should show it. Thanks.
Can you listen it? Yeah, thanks.
Yes. So I'll show it. Yeah. Thanks for pointing that out. So I will choose a different color. Yeah. Maybe red color. See, I'm trying to show the AR translate tau. So the AR translate is this. AR translate of this is this, and the AR translate of these is this. If you remember, then this is projective module at vertex 3, this is projective module at vertex 2, and this is projective at vertex 1, and they do not have translates. The sequence sort of starts with that. So therefore, they do not have any translates, as verified by the theory that AR translates of projectives are 0. And what are inverse Auslander-Reiten translate? Just go along the reverse direction. And if you remember, then Isha was talking about like how we have to maintain all the levels. Yeah, so the Auslander-Reiten translate is always 2 distance apart in the AR quiver, but at the same level. That's how we characterize it. Yeah. And injective modules, if you observe, then there are the remaining 3 modules are injectives. So this is injective module at vertex 1. This is injective module at vertex 2, and this is injective module at vertex 3, and they do not have inverse Auslander-Reiten translates. This theory is beautiful for you can play around with these ideas. You can draw examples and see. Any other questions? Okay.
Apart
Okay.
from Gabriel's theorem, everything depends on the orientation. So, right?
Yes.
Everything
Yes,
depends on
please.
orientation.
Orientation is very important. Yes.
It's merely some special feature of Gabriel's theorem that it doesn't depend on orientation.
Yes. Yes. I don't know. I mean, I cannot put it in words what it is, but Dinkin diagrams are somehow special. So therefore, it doesn't matter what orientation you choose. Okay, so let us look at a simple application. In order to make my speed 0.9, I have left many gaps. I had written this proof and then I erased it so that I can do it live in the class. Okay, so we'll start with any module M. Yeah, so then we have to show that the projective dimension is at most 1 if and only if certain home is 0. So this is very interesting because if you remember, then homes can be calculated by just looking at the Auslander-Reiten quivers. I will remind you how homes were calculated. So if you want to verify which ones this one has maps to, yeah, let's say this one, then you basically take the whole space generated by this and upward as well, but upward there is nothing. So only the things which lie in this, they can have non-zero maps, but it should also, yeah, I mean, you remember this from maybe second tutorial. We covered this part. So homes can be computed. Homes can be just observed. Whether the home is non-zero or not can be observed by just looking at the Auslander-Reiten quiver. So here we are saying that, well, you should be able to do it by just looking at certain homes. Okay. So let us start with the proof. So start with.
Here, A is a specific finite dimensional.
No, A is the
path
ring.
algebra.
A is the ring, right?
Okay.
Yeah. I mean path algebra. Yes.
Okay.
So start with a minimal projective resolution. Minimal projective presentation, not resolution. So 0M, then P0, P1. Okay. Then apply new. Let me call them F1 and F0. So apply new. And what do we get after applying new? You get 0 to tau M to new P1 to new P0 to new M to 0. And all we care about is this new F1, and this is kernel of new F1. But then the idea is apply nu inverse again. Now, so what will happen? Well, nu inverse is left exact. Nu is right exact, so nu inverse is left exact. So therefore, it will preserve the first zero. What is nu inverse? Well, it is home dA tau m. And then nu inverse nu P1, nu inverse nu P0. Well, I don't really care about the last part. And compare it with the original thing. So kernel of F1, then P1, P0, and 0. 0, 0 are equal. And because nu and nu inverse is an equivalence on projectives, so therefore nu inverse nu P1 is isomorphic to P1 and nu inverse nu P0 is isomorphic to P0. Okay, so once we have this, then first of all, tell me why we have a map over here. Why does there exist a map from here to here? Because of some simple category theory that whatever this map
Property
is,
of
you
kernel.
start at. Yes, so home dA tau m, you go to this, then you follow this isomorphism and then P0. Well, obviously this is 0 because this way is 0. From here to here and then down is 0. Therefore, this way is 0. So therefore, there must be a factorization through kernel of F1. So therefore, there exists a map. And then finally, how can you conclude that this is actually an isomorphism? For that, you have to use some result. I mean, you can directly prove this as well, but you can also use a result called 5 lemma. And so this is an isomorphism using 5 lemma. So 5 lemma, how you can visualize there is an isomorphism here, 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 and you can put a 0 before that, or you can directly show that this is an isomorphism. Either method works. Okay, so that's why now just observe. If the projective dimension is less equal 1, then kernel of F1 will be 0. So kernel of F1 is 0 if and only if home dA tau m is 0. Simple. Okay. So now the question that Anay asked. Yeah. So tau, Auslander-Reiten translate tau is not always injective. However, it's injective up to a certain extent. So let us start with two indecomposable modules m and n. So in fact, tau m is 0 if and only if P is projective. So we have seen one side of the argument. The other side also holds true. Then tau m is if m is non-projective, just to ensure that tau m is non-zero, then tau m is indecomposable and tau inverse tau m is isomorphic to m. Yeah, precisely the question that he asked. So for all non-projective ones, you get tau inverse tau to be identity. And as a consequence, you can see that if m and n are both non-projective, then their translates are isomorphic if and only if they were isomorphic to begin with. How to obtain 3 from 2? Well, one side is obvious, the reverse side is obvious. Otherwise, apply tau inverse and you will recover the right-hand side. Okay, so let us try to prove the first one. And so if tau m is 0, then nu f1 from nu p1 to nu p0 is a split map. Do you agree with this? Yeah, I mean, if tau m is 0, then this is a map between two injective modules and it is an injective map. Injective map between injective modules is always a split map. because the source of that map is injective. That is the definition of an injective module. So therefore, nu F1 is a split mono. But because nu is an equivalence, like restricted equivalence, F1 is also a split. And it is a split mono. But split mono by minimality, when can that happen? By minimality, P1 has to be 0 to begin with. Otherwise, because it's split, you can factor out something else, some other part. I mean, is this part clear? What I'm saying is this. So P1 to P0 is a split mono, which means P1 to P0 dash direct sum P0 double dash. Yeah, this is what will happen. This is our F1. Now, obviously, we know that it maps into only one of the components. P1 to P0 dash is an isomorphism. So this can be written as, well, P1 to P0 dash, whatever is the F1, the real F1, and direct sum 0 to P0 double dash. This is not minimal. So by minimality, we can guarantee that P1 is 0, which means the module was projective to begin with. Yes, Irfan?
So why this F1 should map the P1 to one component? I'm not sure.
Because it's split mono. It's a direct sum decomposition of the target. Yeah?
Sure.
Okay. Any other questions? Okay, so minimality is actually helping us quite a lot over here. So let's try to prove the main result here, that if M is non-projective, then tau M is indecomposable and tau inverse tau is identity on such modules. Okay. So here I haven't filled up all the details, but let us see. If M is non-projective, then let us start with a minimal projective presentation. By minimality, F1 is not a direct sum of two maps. What do I mean by that? Again, let me explain it over here, that P1 dash direct sum P1 double dash and P0 dash direct sum P0 double dash. We don't have a matrix where we have F1 dash, F1 double dash and 0, 0. Yeah, this situation cannot happen. That is what I'm claiming. Just by using minimality. Otherwise, you can separate these two things. This minimality's argument is quite crucial, and then we just because of this observation, we can prove that tau m is indecomposable. Because if it is not, then the minimal injective presentation of tau m, yeah, which is 0 tau m nu p1 nu p0, that yields that nu f1 is a direct sum of two maps. Yeah, because there should be something separate for x and something separate for y. So which means that map is a direct sum. Nu f1 is a direct sum of two maps, which means f1 is a direct sum of two maps, which we already observed is not. So therefore, x and y both can't be non-zero. And that's precisely what we wanted, that because nu is an equivalence. However, there was something that I did not say explicitly. Yeah. Did you observe something that I just swept under the carpet? Okay, it is in this star. Yeah. So star is definitely an injective presentation of tau m. But why is it minimal? Yeah, so I mean, minimality of the projective presentation is the reason why this is also minimal. Okay, so nothing changes really over here as well. Yeah, the same argument works. Okay, now let us try to finish the proof. We have established that tau m is indecomposable, so apply nu inverse to star, and what do we get? Well, nu inverse tau m to nu inverse nu p1, which is p1, this is p0, and this is tau inverse tau m to 0. So what do we know? Well, whatever this map is, tau inverse tau m is just the co-kernel of that. But nu inverse nu f1 is just a map between two projectives, the same old projectives, which is just f1, which was m to begin with. So therefore, we get the isomorphism. Any questions? Okay. So 3 just follows from 2. And here is a scholium. Yeah, scholium is corollary of a proof. You don't often see this term, but we use some technique over here. So if m is non-projective, then tau m has no non-zero injective direct summand. You just need to observe that. The argument is again minimality. Yeah, so at the step star itself, I argued that this is a minimal projective resolution, minimal injective resolution. So it just follows from that. Yeah. If it had a non-zero injective direct summand, then that injective will have identity into itself, and then the corresponding map would be that injective to 0. That will be a direct sum. So it contradicts minimality. So what we are saying that if we start with something non-projective, then we'll obtain something which doesn't have any injective direct summand. In general, if we start with something which doesn't have any projective direct summand, then you end up with something which doesn't have any injective direct summand. Yeah, lots of negatives while talking about this. Okay. So tau annihilates projectives. Yeah. It is not an equivalence, but can we obtain an equivalence from this? Can we at least restrict, or can we induce an equivalence? And the answer to that question lies in stable categories. So here we are going to revisit the concept of the ideal. Yeah. So let us see this. So let M and N be two modules, and let PMN denote all those morphisms from M to N which factor through a projective module. So for example, zero map always factors through a projective, namely the zero object, zero module itself. Okay, so this PMN, because I have written this notation, it better have some good properties. So the first good property is that it is closed under scalars. Obviously, if F factors through a projective, then lambda F will factor as well, the same projective. If F1 and F2 both factor, then F1 plus F2 also factors. Well, look at the idea. If Fi is HI-GI, where the target of GI is projective Pi, then I can write F1 plus F2 as a product of these two matrices. And the middle object of this factorization is P1 direct sum P2. And therefore, it will factor through a projective. So this is also closed under sums. Locally, it is a K subspace. That is what we have shown so far. And finally, just notice that if you have a sequence, a composable sequence of 3 arrows, where the middle one factors through projective, then obviously the whole composition also factors through a projective. So therefore, what do these three properties say together? What does it say about P, the collection P of morphisms? Any idea?
That's an ideal.
Yes, it's an ideal. Yeah. Ideal, or you can also say it's a congruence relation. Yeah, congruence relation is something which behaves well with respect to, just hold on. Yeah. So the campus, the The congruence relation is something with respect to which you can quotient a category. To obtain quotient categories, you need especially this third condition. The first two are just there because we are talking about additive categories. Otherwise, the third one is really the definition of a quotient congruence relation. And we can take this quotient of the module category by P and we obtain this A mod, where I have underlined mod. Yeah? So this is the stable projective category, projectively stable category. And dually, you can define the injectively stable category, which is all the morphisms factoring through injectives, and we write it with mod top, like a bar over mod. And there is this theorem whose proof I'm not going to cover. Yes.
I have a small. So the left-hand side, that underline was a notation, and the tilde on the right-hand side is just a decoration, right? I mean,
Tilde is just the decoration. Yeah, I want to specify that it's a category. Oh. Yeah. Yes, I have been using that notation consistently for all the categories, for writing all the mods so far.
But actually, essentially, the point underline bar is a notation, right?
Yeah, underlined bar is the notation, which means it's projectively stable category, and overline is the injectively stable category. Okay. So A mod to A lower mod to A upper mod, tau and tau inverse actually gives you a perfect equivalence. Yeah, so we just like whatever was bad, we quotiented that part out. And we are going to return to this part eventually while doing Auslander-Reiten formulas. Okay. And the proof here uses a short exact sequence of categories where the middle object, that the one that covers a mod, is the category of arrows in a project. I mean, just to briefly tell you, this idea actually comes from K-theory, where we talk about morphism, category of morphisms between projectives. So the arrows are the objects and commutative squares are the morphisms. And yeah, it's a long proof. And if you are interested, you can look it up. It's in Assem's book, not in Schiffler's book. Actually, Schiffler's book is very short. It doesn't have a lot of content. Yeah, but for a first course, if you want to, I mean, I'm also doing the same thing essentially, that I'm leaving out most of the proofs. But still, I believe that reading Assem's book would, Assem Simpson's Koronsky, that will give you better understanding of the material, although it's very long. Okay, so what is the use of doing all these things? So the use of Auslander-Reiten translate is to obtain, given any non-indecomposable, non-projective, we would like to obtain a non-split exact sequence of this particular form, which ends at M, begins at tau M. That tau M exists because it is non-projective, and then E is some extension. Well, that extension is actually uniquely determined. Again, I don't think we'll have time to look at the proof of this result, but at least I will convince you that there exists something like this. Yeah. So existence and definition of these things is still remaining. Existence will be a consequence of the Auslander-Reiten formulas. And well, what is this definition? Like, why is this particular type of sequence important? Well, let us look at that. So split sequences in some sense are the best ones. Yeah, there is something in the chat, it seems. Yes, Tanisha, which second reference? Assem-Skoronsky, Simpson-Skoronsky. That's already in the folder. Yeah, you just go to the folder, it's already there. Okay, so this a short exact sequence is said to be a split exact sequence if either F is split or G is split. I mean, F has to be a split mono or G has to be a split epi. Yeah, so mono and epis. In fact, if you have one, then what happens? Yeah, then the middle object is isomorphic to x direct sum z. Yeah, whatever this y is immaterial. Up to isomorphism, it is just x direct sum z. This first map is 1, 0, and projection map is the projection onto the second component up to isomorphism. And you should remember this particular type of diagram. Yeah, what diagram? That in the first component I'm taking equality, in the second component I'm taking equality, and in between I'm taking isomorphism. So these types of diagrams which tell you equivalence between two short exact sequences will be important tomorrow when we do extensions and X1 group. Yeah, so this hash types of diagrams are important. Okay, so split sequences are the best sequences. Yeah, you don't have to worry at all. Everything is nice. But what is the next best thing that you can do? Those are almost split sequences, which means essentially, yeah, that every other short exact sequence will somehow factor through this next best thing. And almost split sequences or Auslander-Reiten sequences can have to be defined using some slightly technical machinery. Yeah. So we say that a morphism is left minimal. So there are two properties we need on these morphisms: left minimality and left almost split. Yeah. One of them is quite natural if you think about it. Maybe let's do that. The second one first. Yeah. So say that F is a left almost split morphism if it is not a split mono. Obviously, it's not a split mono. But if you are given any other morphism which is not a split mono, then it will factor through F. Okay, so it is not a split mono, but any other morphism which is not a split mono will factor. So this is in some sense universal amongst the non-split ones. Of course, the split morphism won't factor here. Yeah, so this has the universal property of this kind. However, if I'm given some L and then I ask, does there exist a unique left almost split morphism? The answer is no, not in general. For that, you have to pair it up with something else. And that property is this left minimality. So we say that a morphism is left minimal if whenever an endomorphism H satisfies HF equal to F. So H doesn't really touch the image of F. Yeah, that's the loose idea over here. Then actually we can conclude that H is an automorphism. So the only endomorphisms which move around the image of F are in fact automorphisms. Which fix the only endomorphisms which fix the image of F are automorphisms. So if we take these two conditions together, then we'll get uniqueness of the left minimal almost split map, which means the combination of both of them. So let us see the proof of this very quickly. Suppose L to M1 and L to M2 are both left minimal almost split maps. So this is F1 and this is F2. Using the left almost split property of F1, we know that there exists a map H1 in this direction such that the diagram commutes. And using that F2 is left almost split, we know that there is something which is like this. And then this is a standard argument in using categories. Now you have endomorphisms, yeah? H2, H1 is an endomorphism. What will happen with H2, H1? H2, H1, F1 is equal to F1. Therefore, H2, H1 is an isomorphism. Is an isomorphism. And similarly, you can conclude that H1, H2 is an isomorphism and therefore they are inverses of each other. So which means M1 and M2 are in fact isomorphic such that the diagram commutes. So uniqueness up to isomorphism is possible if you take a combination of these two. Any questions? Okay. So if L to M is a left minimal almost split morphism, then L is indecomposable. So we are getting a lot of things. So what we are trying to do is essentially characterize the first morphism of an Auslander-Reiten sequence. So L has to be indecomposable. So let's see. If L is not indecomposable, so L1 and L2 are non-zero, so L is isomorphic to L1 direct sum L2, then there is a morph. So L to L1, there is a morphism, which is simply the projection. And for this projection, can you tell me why it is non-split mono? I mean, it is not a split monomorphism. Do you agree with that? Like it's not a split monomorphism, it's a projection map and L2 is non-zero. So therefore, this is not a split monomorphism. So there will exist some F1. And similarly, if you replace L1 by L2, there will exist some F2. And then you just rewrite this. Yeah, you take L1 direct sum L2 here and you write it as a matrix form. And identity can be factored through F, which means F is a split mono, a contradiction. Okay, so therefore, you can conclude that the domain of a left minimal almost split map is indecomposable. Any questions about this? Okay. Then let us look at an example. Yeah, we already discussed the radical today. So the inclusion of the radical into the module is right almost split. Okay. So why is it right almost split? Well, start with this J over here and take any morphism which is not a split epimorphism. Then we have to show that there exists such a map. So because it is not a split epi, and I'm using another notation, AEI is essentially the same thing as PI, yeah, the projective module PI. So because it is not a split epimorphism, it is not even a surjection. Can you tell me why? Not split epi implies it's not an epimorphism itself. Well, I'm feeding too much information. There is brain fog for audience. Yeah. Okay, so just remember that AEI or PI is a projective module. So any epimorphism splits. So therefore, if it is not a split epimorphism, it is not an epimorphism itself. Okay. So once you have that, then therefore X will sit inside the, like the image of H will sit inside the radical. I told you, at least in our bound quiver case, that the codimension of this radical is 1. So because it is proper, because image of H is proper, it must sit inside the radical, which means there is a factorization through the radical. Got the idea? Why it is right almost split? And moreover, it is also an irreducible map. Yeah, irreducible, you might remember, it is not a split morphism, and it is not like if at all you can factor it, then either the first component is split mono or the second one is split epi. That was the definition of an irreducible map. So now consider this inclusion J again. You try to factor it from F to Y, like as GF. What can you say about F? Because J is a monomorphism, F is a monomorphism. Basic category theory. And by maximality, yeah. So maximality of the radical inside the collection of submodules, yeah, maximal proper submodule, either F is a split mono or G is a split epi. Yeah, so do you understand what I'm saying? That if at all, so F is a monomorphism. So F, what will be the image of F? It has to be something which lies between the radical and the projective module itself. But because it's maximal, there is nothing in between. So either it is the radical itself, in which case F is an isomorphism, or it is the full thing, in which case G is an isomorphism. So done. So the inclusion of the radical of a projective inside the projective is an example of an irreducible morphism. So you have got several examples now. However, at this point, you should also notice that the radical need not be indecomposable. We saw this example, yeah, some time ago. Let me recall something. I was writing that J1, yes, J1, J2, J3. Yeah, radical here was a direct sum of 2 copies. So an irreducible morphism is not necessarily only between indecomposables. Okay. So we have one example of a right almost split and one example of an irreducible map. The same example works. And dually, if you take an injective module and quotient out by the corresponding simple module, which is the dual of taking radical, it's the co-kernel of that inclusion from SI to II. This is a left almost split map and also irreducible. This is just the dual proof. Yeah, I mean, our whole theory is self-dual. That's the beauty of this whole thing, that projectives go to injective, injectives go to projectives. You just have to reverse the direction of arrows. Okay, so yeah. So just to give you some flavor of properties of these irreducible morphisms. So given a non-split exact sequence like this, the following are equivalent. I will only prove one direction of this, that F is irreducible. The first map is irreducible if and only if for any map to the last thing, yeah, quite unusual to think about this. Yeah, we are talking about this map F being irreducible, and then for any map H from X to N, either the green arrow exists or the gray arrow exists, so that the diagram is commutative. Okay, so 2 to 1 I have left as an exercise because it uses some advanced machinery from categories. I don't want to talk about it. But first one, perhaps we can do, yeah, this particular thing. So what we have is this 0 LMN, and we have this morphisms F and G, and we have morphism H. Well, what can we do? If we are given this kind of situation, we can do the only possible thing is taking the pullback of G and H. Pullback or fibered product, I mean, are people familiar with this? No? Okay, so basically, okay, let me write this. Let me mention that this is how we write this, and the definition is this. Yeah, all those tuples x comma m in x cross m such that hx is equal to gm. Yeah, so this is the set theoretic description of what the pullback is. So it is a subset of the product. And obviously there are natural projection maps. This is the first projection, and this is the second projection. Yeah. And well, there is a property of abelian categories. We have been saying that several times, that because G is surjective or epimorphism, pi1 is also surjective. So therefore, we'll get a 0 over here. So we constructed a pullback, and we noted that one arrow in that pullback is surjective. Now just observe, yeah, I can take a map. Yeah, what is the property, universal property of the pullback is that whenever you have a pair of morphisms from like to these two important things, yeah, those two are the starting points of the pullback, yeah, starting points of the legs of the pullback. So if there are two morphisms, namely I'm taking the 0 morphism from L to X over here and morphism F from L to M, and observe that H composed with 0 is G composed with F. G composed with F is 0, yeah, because it's an exact sequence. So therefore, there must exist a factorization, unique factorization through the pullback. Well, which is what I'm writing over here. Yeah, there exists a unique factorization. Let me call that F dash through the pullback. Are you still with me so far? Yeah. So now we have obtained a monomorphism. Now, then you have to argue that this is a monomorphism. Why it is a monomorphism? Because I think just the pullback property will tell you why it is a monomorphism, and therefore the top row is also an exact sequence. The bottom row was given to be an exact sequence, and X to N map was given, and we have concluded that the top row is also an exact sequence. So what have we obtained really? We have obtained a factorization of F. Yeah, so F is, so let me write that. So F is equal to pi2 composed with F dash. And we are assuming 1, which means F is irreducible, which simply means that either pi2 is a split AP or F dash is a split mono. If pi2 is a split AP, yeah, then the red arrow will exist. Okay, let me find red. Yeah, the red arrow will exist, which, I mean, from M to X, that red arrow will give you a map such that the triangle commutes. Or else the gray arrow will, a green arrow will exist, which is this. F dash is a split mono. Well, we haven't completed the proof, have we? If F dash is a split mono and the top row is an exact sequence, then it is a split exact sequence. So the other green arrow will also exist, with namely this. Both maps are split together. So in that case, you will have a map from X to M. Okay. So we have proved that 1 implies 2. A slightly involved proof, but this particular thing can be used to show that if F is an irreducible monomorphism, then its co-kernel is indecomposable. I'm not going to do this proof, but yeah, so I'm going to end it here by just noting that an Auslander-Reiten sequence is one where the first map is left minimal almost split and the second map is right minimal almost split. And we'll find several characterizations of this. And there will be some more properties of these irreducible maps, etc. will be discussed. Any questions?
So this corollary is going to tell us projective modulo the radical is indecomposable.
No.
Is that the reason?
No.
Okay.
Corollary says that if you have an irreducible monomorphism. Oh,
Yeah,
okay. The
inclusion of radical.
co-kernel is indecomposable. Co-kernel is just one-dimensional there, so that is indecomposable anyway.
Oh, that's just simple at
Right.
simple
Right.
at